to the geometries that have a Hermitian form and also holomorphic form, which are not necessarily closed. These non-Kähler geometries appear naturally in the context of heterotic string theory and type 2 string theory in the presence of fluxes. For example, in the compactification of heterotic string theory to 4 dimensions, the internal 6-dimensional manifold can become non-Kähler in the presence of 3-form fluxes. Various models of building heterotic manifolds and vector bundles on them have been put forward. These have been analyzed by Strominger, Becker, Yau, Fuzhen, Anderson, and many other physicists and mathematicians. These play an important role in searching for realistic standard model-like physics in 4 dimensions. An interesting type of non-Kähler manifolds are the Hermitian balanced manifold. These balanced manifolds have Hermitian form and also holomorphic form. The Hermitian form for a non-Kähler balanced manifold is not closed. However, there's a nice property. The Hermitian form omega raised to the power p minus 1 is closed, where p is the complex dimension of the balanced manifold. There are also other nice properties of the balanced Hermitian manifold. Some of them can have trivial canonical bundle, and these are also non-Kähler Calabi-Yau manifolds. Another nice property is that under appropriate blowing downs or contractions of curves, some non-Kähler balanced manifold can become Kähler and projective and can be studied by algebraic geometry. A very interesting type of non-Kähler Hermitian manifolds are the twisted spaces of 4 manifolds. In particular, the self-dual 4 manifolds. Here, M4 is the self-dual manifolds. P1 is the twisted fiber, and Z is the twisted space. For the self-dual 4 manifold, most of the twisted spaces of them are not Kähler, unless M4 is S4 or P2. For example, an interesting class of self-dual 4 manifolds are the MP2s, which are the connected sum of n copies of P2s, the projective planes. N equal to 0 stands for S4. For n equals to 2 or 3, the structure of the twisted spaces of these MP2s were analyzed by Pohm, and they are non-Kähler. Most of them also have a balanced metric. For n greater or equal to 4, the situation becomes more complicated. However, Lebrun showed there exists an explicit conformal structure for all the MP2s. Here, we can make a branched double cover of these spaces, branched along appropriate divisors. Let's consider more details the branch covers. Here, M4 is a double cover of X. Consider a divisor D inside X, which corresponds to the 0 of a section of a line bundle. Then the canonical class of the branch cover is this, where D is the divisor class of the branch divisor. Under this branch covering, the twisted fiber P1 also gets double covered. The P1 intersects with the branching divisor at discrete points. So P1 branched along these points and become a Riemann surface of genus G. Choosing different branch divisors will give rise to different branched covers. There are 2 interesting types. If choosing the divisor class to be the canonical class of the X, then the resulting branch cover has T2 fiber. And the second type is that we can choose the divisor class to be twice the canonical class of X. The resulting branch cover, by the adjunction formula, has a trivial canonical bundle. Hence, these are also non-Kähler Calabi-Yau manifolds. And the above two type of branch cover were analyzed with collaborators Heckman, STL, and in another work with BU and STL. Now let's consider more details of the branching devices. There are two situations. The first situation is that there is a single smooth divisor D. The branched cover M branching along this divisor is smooth. And the divisor class is in trisect canonical class, so the M is have a trivial canonical bundle. There's another situation where D is a normal crossing divisor. Here we consider D as a union of two components, D1 and D2. D1 and D2 intersect at C, a curve. The branch covering along this divisor have singularities along the pre-image of the curve. One can make a small resolution to arrive at the final smooth threefold M, which also have a canonical, trivial canonical bundle. This procedure has another equivalent view. We can first blow up along the curve C, and then the proper transform of the D, which is D tilde, become union of two disjoint components. And branching along D tilde produce a smooth threefold, which is the same as the above construction. The procedures are equivalent. One can see that for the Triss space of MP2 with the Lebrun's conformal structure, the choice of the canonical class indeed defines divisor that is a smooth divisor or a simple normal crossing divisor. In the above construction, the branch covers are non-Kähler and also have trivial canonical bundle. These are non-Kähler Calabi-Yau manifolds. The non-Kähler Calabi-Yau manifolds here are the manifolds with trivial canonical bundle, but are not Kähler. We can also construct various vector bundles of them. Now let's consider the existence of balanced metric on branch cover. An important way to analyze whether a P complex dimensional manifold is balanced is by using a lemma by Michelson. If there exists a P minus 1, comma P minus 1 form, which is closed and positive, then this is equivalent to that the manifold has a balanced Hermitian metric. This is lemma by Michelson in 1982. Now, for the Triss space of MP2 with Lebrun's conformal structure, there's balanced Hermitian form omega z, which is closed positive 1-1 form. And omega z squared is a closed positive 2-2 form, which can be used in the Michelson's lemma. For the branch cover M, we can pull back this omega z squared onto the branch cover. And the pullback of this 2-2 form is positive away from the branching divisor. Near the branching divisor, we need to make modifications. Consider a line bundle L on M. It has a Hermitian metric H, and its term form is positive on the neighborhood of the branching divisor. So C1 squared is positive on the neighborhood U. On the other hand, C1 squared is bounded below in other locations. The pullback of omega z squared is positive on the complement of U in M. Hence, we can find a sufficient large constant C to make this combination. And this is strictly positive and closed 2-2 form. And by Michelson's lemma, the branch cover has balanced metric. There's other ways of constructing non-Kähler manifolds. Fu Yao, Goldstein, Prokrushkin constructed T2 bundles over four-dimensional Kähler manifolds. They give rise to interesting non-Kähler manifolds in 6 dimensions with balanced metric. Here we can also consider using T4 fibrations analogous to the T2 fibrations. And this is a geometric model for 8-dimensional manifolds. The 8-dimensional manifolds and the 6-dimensional manifolds are both very interesting. They have similarities in the mathematical structures. For example, they can both have SUN structures. Also, the Hermitian balanced manifolds exist in both 6 and 8 dimensions. Here, the 8-dimensional manifold with SU4 structure can include both the usual Kähler-Calabi-Yau fourfolds and also other non-Kähler Hermitian manifold with SU4 structure. In a later case, they can be also realized in string theory in the presence of fluxes, in which the Hermitian form and the holomorphic form need not be closed. Here, this is the model of T4 fibration over Calabi-Yau twofolds, which I analyzed. Consider 10-dimensional metric as a word product of 1+1 Minkowski space and the M8. The M8 is a T4 fibration over the base M4, where pi is the projection map. The theta 1 and theta 2 are 1 forms with the connections A1 and A2, which are pullback of 1 forms on the base M4. Those are 1, 0 type forms with curvature in the H2 of M4. The holomorphic form of the MA is theta 1 wedge theta 2 wedge the pullback of the holomorphic form of M4. And the Hermitian form is not closed or conformally closed. So the MA is not a Kähler manifold and is not a conformally Kähler manifold. This is due to the non-trivial fibration of the T4. Let's consider some simplifications. Consider M4 to be Kähler, and we assume the condition for the F. Then we find that there's a conformally closed positive 3-3 form. So by Michelson's lemma, this means that MA is conformally balanced. The curvature of the connection by these conditions, and this translates to that F are in the space of anti-self-dual 1, 1 forms. There's another nice property, which is that when the M4 is Calabi-Yau twofold with SU2 structure, then MA has SU4 structure. The model of T4 fibered over Calabi-Yau twofold can be embedded in type 2B string theory. And the metric answer is the same. The fluxes can be decomposed in this way, where F is the sum over R fluxes with different ranks. The 10-dimensional Killing spinors can be decomposed, where zeta is 1+1 dimensional Weyl spinor, and eta 1, eta 2 are 8-dimensional Weyl spinors. There exists a pure spinor eta, which is proportional to eta 1 and eta 2, and the SU4 structure J and omega can be constructed by the spinor bilinears of eta. One can construct 2 polyforms by the J and omega. Prince, Simpis, Rosa derived very elegant equations of the pure spinors from the supersymmetry equations. And this was also discussed by Lust, Patalon, and Simpis. From the pure spinor equations, we can see that F3 is related to the DC of the Hermitian form with appropriate factors. And due to the self-duality of the fluxes, there's another equation which relates dCj with dj squared by a Hodge duality in 8 dimensions. The case with constant e to the 2a and e to the 5 was analyzed by Minasian and Prince. There are special solutions when the dilaton is related to the warp factors in these ways. Then dF3 is non-zero. It is given by the curvature squared, and also the Laplacian of the dilaton. On the other hand, dF3 is given by the sources in type 2b string theory. Those are fibrins with positive charge or negative charge. The existence of the negative O5 was anticipated by Grenier, Minassian, Petrini, Tomasiello, and others. So the above is a configuration with F3, F7, and the dilaton in the warped product of two-dimensional Minkowski space and MA in the type 2b theory. So these non-Kähler geometry with T4 fibrations would be useful for mirror symmetry for non-Kähler A-dimensional manifolds. The non-Kähler mirror symmetry for A-dimensional non-Kähler manifold was proposed by Laozhen, Yao, and analyzed in string theory by Minassian and Prince recently. The T4 fibration here is analogous to the T3. It might be interesting to perform T-duality transformations along the T4. We have discussed about the Church space of self-dual four manifolds. There are also other Church spaces. For example, the Church spaces of hypercomplex manifolds and the hyperkähler manifolds. These are very interesting. The hypercomplex manifolds are generalizations of the hyperkähler manifolds. They have three complex structures. They have a two-sphere worth of complex structures. The hypercomplex manifold has associated Hermitian forms which are not closed. The Church space of the hypercomplex manifold has a smooth structure which is M cross P1. On each point of P1, on this Church space, there is a hypercomplex manifold M4 whose complex structure is given by the corresponding point on the P1. The Church space of hypercomplex manifold is balanced. This can be seen by a lemma by Thomburg. Consider M to be an n complex dimensional hypercomplex manifold. Then one can find a strict positive closed form with this combination, where omega m is a Hermitian form of the hypercomplex manifold. This is the n comma m form. Hence, by Michelson's lemma, the Church space Z is balanced. In the following, I will describe an analog of the Church spaces of hypercomplex manifolds in higher dimensions by changing the Church P1 to a high-dimensional complex manifold Q. Consider a holomorphic subimmersion H from Q to P1. Q is a complex manifold with complex dimension R, and M is a hypercomplex manifold. The high-dimensional analog is X, which has a smooth structure, M cross Q. X is a complex manifold. Let's consider the complex structure of M. The hypercomplex manifold has complex structures IJK related in these ways. The complex structure of X is given by this, where the first part is a linear combination of the complex structures on M, and the second part, I, is a complex structure of Q. X is a Hermitian manifold. The Hermitian form of M is also a linear combination of the Hermitian forms associated to the three complex structures on M. Q is complex and equipped with a Hermitian form omega Q. X is complex, but it needs conditions. We find a lemma that there's a necessary and sufficient condition for X to be complex, which is that the H is a holomorphic map. the Q can have complex dimension R, which can be greater or equal to 1. So when the complex dimension of the Q is 1, this is the case where the Q are Riemann surface. And these were analyzed by T. Fei. In this case, the Q is also branch covering of the just P1. See also related discussion in the case where G equals 3 or G equals 1. In the following, I will describe the balanced Hermitian form on the high-dimensional analog of the Church space of hypercomplex manifolds and on their branch covers. Consider H tilde from X to Z, and we can make a branch covering of X to produce X tilde. F tilde is a composite map of H tilde and F. The branching divisor is D. D and Q intersect at S. S has component Si. For each Si, we can find a local coordinate Ui parameterized by Z1 to Zr. Ui is locally Si times C, where C is parameterized by Z1. One can find a positive NM4 by using a real smooth function. And near the neighborhood Ui, the n comma m4 becomes this. And this is strictly positive near the neighborhood Ui. On the other hand, we can have a combination of these two terms, which are strictly positive and closed away from the branching divisor. Near the branching divisor, the third term is strictly positive. So we find a combination of these three terms that are closed and also strictly positive in all the locations. One can also construct a 1, 1 form, omega tilde, by raising omega tilde to the power n plus r minus 1. The X has complex dimension n plus r. The existence of capital omega, which is m minus r plus 1 comma n plus r minus 1 form, which is closed and strictly positive, by Michelson's lemma, implies that the X and its branch cover X tilde are balanced. So these are the major conclusions of my talk. Thank you. CY2.
Instead of if we consider F theory, then what can we say?
You mean generalizing T2 to T4?
The F theory.
Yeah, you mean possible duality between this manifold to other string frame? Indeed. Right, so suppose we consider K3 fibered over K3, then they can be mapped to T4 fibered over K3 in heterogeneous string theory.
But, for example, in the case of F theory, the torus fiber can be degenerate.
Right, and they can also be due to, the F theory setup can also be due to the heterogeneous string theory with the T2 fibers.